Welcome to the 20th lecture of combinatorics. In the last class we stopped at this simplified situation where we can apply the inclusion exclusion principle. The general case was discussed before. Now the simplification is that suppose your universe is of cardinality alpha 0 and any pair of any singleton set, okay, here any singleton set is of cardinality alpha 1 irrespective of which set, all singleton set any AI is of cardinality alpha 1 and any pair has cardinality alpha 2 and any intersection of any pair means for instance AI and AJ, if you take irrespective of which I and J, their intersection has cardinality alpha 2 and any triple for instance IJK, if I take irrespective of which is this IJ and K, AI intersection AJ intersection AK always have cardinality alpha 3 and so on, right. In that case the formula simplifies. Here in this case I have made a mistake in this slide. So what we want is the complement of this, the cardinality of the complement of A1 union A2 union AK is what we meant. So of course, so right, I will write correctly. We want A1 union A2 union AK, the complement of this, what is the cardinality of this. So we have seen that this is same as A1 complement intersection A2 complement intersection, so AK complement, right. This is cardinality of U minus sigma I equal to 1 to K, the cardinality of AI, right, minus plus sigma for every pair IJ, if I take AI intersection AJ cardinalities and minus, like that we had written the formula. But here we know each of, look at this term, each AI here has cardinality alpha 1. So this cardinality is alpha 0, this each has cardinality alpha 1, therefore total here is K choose 1 into alpha 1, k times alpha 1, we can say k choose 1 times alpha 1. Similarly here every pair, each of this irrespective of which I and J I am talking about, the cardinality here is alpha 2. So total here will be k choose 2 times alpha 1. So you can use a different color, k choose 2 times alpha 2 for this thing, right. So this is k choose 1 times alpha 1 for this, and this is alpha 0. And here the next term, when I, J, K are considered and AI intersection, say, so AI intersection AJ intersection AK is considered. So this always is alpha 3 irrespective of which IJK I am talking about. So therefore this total, this sum will be how much? So K choose 3 into alpha 3, right, K choose 3 into alpha 3. So we can rewrite this as, so alpha 0 minus K choose 1 into alpha 1 plus K choose 2 into alpha 2 minus K choose 3 into alpha 3 and so on until minus 1 raised to K. See, K choose K into alpha K, right. This is not required now because we know this is just 1. So we can remove this thing. So we can just say into alpha K, right. This is the formula. This is nothing non-trivial, definitely there is, it's quite easy thing. You just have to observe that when in a summation, when every term that is summed up, everything that is summed up is of equal value, then we can just multiply by the number of terms in the sum, right. That is what, for instance, in the first sum we have k choose 1 terms, in the second term we have k choose 2 terms, in the third sum we have k choose 3 terms and all, that is all, right. Now you see, why do we write it as a special case? We could have anyway remembered the earlier formula, and definitely we could have applied it whenever we wanted, because this we would have identified, that is true. But again, in many cases, the situation is like this, because the cardinality of say some t sets taken out of the k sets we have, their intersection cardinality will only depend on what is this t, not on which t sets are selected. For instance, in the next example we will illustrate it. Let us see. So let us look how many integers between 0 and 99,999 inclusive, both 0 is also included and 99,999 is also included, have among their digits each of 2, 5 and 8, right. So we are considering numbers from 0 to 99,995. See, of course, one may worry that there are, like, first we have 1 digit numbers, then we have 2 digit numbers, right. 10 to 99 there are 2 digit numbers, then from 100 to 999 they are 999, they are all 3 digit numbers, then we have 1000 to 9999 we have 4 digit numbers and so on. But then we do not have to worry about all those things. We can think that the first number is just 00 by padding like 000000, 5 zeros we put for the 0. For instance, a number like 100 can be padded with 2 zeros in the front, and we can make it 5 digit number, because that way we can say that anywhere I can, there is no restriction, in each position I can use a 0 to any of the digits 0 to 9, 10 digits we can take, we can use, this is what. So therefore, if you ask how many numbers are there, right. So it is just easy to say it is, because there is a 5 digit number, and then we can fill here anything from 0 to 9. So there are 10 possibility to fill this thing, and then here there are again 10 possibility to fill, and there are another 10 possibilities to fill here, another 10 possibilities to fill here. So therefore, the total number is the possibilities are 10 raised to 5. It is quite easy to verify also, because starting from 0 we reach 99,999. So total numbers, total number of numbers we have is 10 raised to 5, of course 10,000, right. Sorry, 10 raised to 5, sorry, 1 lakh, right. This will be the number. So this many numbers are there, right. Now the question is not that how many numbers are there is not the question. We want the number of numbers from 0 to 999 satisfying this following property, which is the following property, namely we should have, we should have 2, 3 and 8 in the numbers, right. For instance, a number like this is not acceptable, we do not want it, we want 2, 3 and 8 in the numbers. For instance, if I consider a number like 238, this is fine, or 210 238, sorry, 21038, this is also fine, or 23008 is fine, right. But not a number like 98765, this is not fine, right. So how many numbers are there like this is the question, right. So is it enough to find out in how many, like how will we solve this thing. So, a direct approach would be to count those numbers which have these thing, but then we will find out, okay, maybe in the first position 2 appears or second position 2 appears, but then 3 can also appear in the first position, and the issue is that they all should appear together, right. So, yeah, one can try to solve it directly, but again if it is a bit complicated, but I would say before trying inclusion exclusion principle to solve this thing, the student can make an attempt to solve this thing whether and map see whether his answer is matching with the answer which we get by inclusion exclusion principle. I do not spend time explaining like why it is difficult and things like that. So, but it is up to you, you can try, but our intention here is to see how we can apply the inclusion exclusion principle to solve this thing. So, as usual we take the universe as these numbers from 0 to 9999. So, this set, this is our universe. So, there are cardinality of the universe is then, so okay, this is not just because according to notation 0 is not included here, therefore, we will include 0 is also 0 also, and therefore, the cardinality of u is equal to 10 raised to 5 as we already noted. And now, we will define certain properties. P1 is the property that the number does not contain, does not 2. So, for instance, when I say P1 of n, that means this number n, when you write it out, it does not have the digit 2 in it, right. For instance, P1 of n will be satisfied by say this number or maybe this number, right. All these numbers will satisfy P1 of n because those numbers do not have 2 in it, right. We are only considering numbers from the universe, say 0 to 99,999, and yeah, similarly we will define P2 of n to be the property that the number n does not have the digit digit 3, right. And then similarly P3 of n can be defined as n does not have the digit 8, right. So, now we can also define the corresponding sets as we are always saying A1, A2, A3. A1 is the set of numbers which has property P1n, P1, and this will correspond to the set of numbers from from the universe 0 to 99,999 having property P2. Similarly, A3 will be the set of numbers in that range in that from that universe having property P3, namely the numbers which does not have the digit 8. So, the cardinality of A1 is easily calculated, similarly A2 and A3. So, how do you calculate the cardinality of A1? That is easy because you just need to make sure that we do not have 2 among the digits of the numbers. We are talking about 5 digit numbers. That means in the first position we have only 9 choices now. Earlier we had 10 choices. Now 2 is not allowed. So, now we have choices are 0, 1, 2 is not there, 3, 4 up to 9. So, there are 9 choices here. Similarly, for second digit position also we have 9 choices, third digit position also we have 9 choices, fourth digit position also we have 9 choices, and fifth digit position also we have 9 choices. Clearly, because now 2 is not allowed, so we can never write 2 here or here or here. None of the 5 digits we can write 2. We can only use 0, 1, 3, 4, 5, 6, 7, 8, 9. Only 9 of them. So, the total number is 9 raised to 5, right. So, the cardinality of A1 is 9 raised to 5. So, this easily the same technique will tell us that the cardinality of A1 is equal to cardinality of A2 is equal to cardinality of A3 is equal to 9 raised to 5, right, because it does not matter whether 2 is not allowed or 3 is not allowed or 8 is not allowed, because one of the digit is not allowed is what is the gist of this argument here. Therefore, each of those cardinalities, when we are not allowing 2 among the digits, or when we are not allowing 3 among the digits, or when we are not allowing 8 among the digits, the total number is always 9 raised to 5. Here is one example where all AIs have equal cardinality, right. And similarly, let us see whether it will extend to 2 pairs of sets. For instance, if I take A1 intersection A2, what does it mean? We are talking about the numbers in from the universe. So, that means from 0 to 99999 such that it does not have 2 among its digits and it does not have 3 among it. 2 and 3 are not allowed. Now, clearly again we use that these are the 5 digit the positions of the 5 digits. The first position now can be filled in only 8 ways. Why? Because 1 is allowed, 0 is allowed, 1 is allowed, but 2 is not allowed, 3 is not allowed, right. Now, 4, 5, 6 up to 9 is allowed. So, total 8 possibilities. Similarly, here also 8 possibilities are there, here also 8 possibilities are there, here also 8 possibilities, here also 8 possibilities, because 2 and 3 are not allowed. So, 8 to the power 5 is the cardinality of A1 intersection A2. And of course, the same is the cardinality of A1 intersection A3, because if you say the digits 2 and 8 are not allowed, that is the same argument, right, because it say at this digit position we have two of the digits from 0 to 9 are not allowed. That is all we have to worry about. So, therefore, we get that A1 intersection A2 cardinality is equal to A1 intersection cardinality A1 intersection A8 A1 intersection A3 is equal to A2 intersection A3. All the 3 2 selections of 2 sets, right, their cardinalities are all same. These are all 8 to the power 5, right. Now, you say what is the third one? A1, A2, A3, there all the 3 together, their intersection. Is this easy to find? Of course, because this is again we see that 5 digit number is to be made, and then this says that I do not allow digit 2, and A2 means we do not allow digit 3, and this says digit 8 is not allowed. Here we have only now 0, 1, 2 is not allowed, 3 is not allowed, 4, 5, 6, 7, 8 is not allowed, 9 is allowed. So, now you know 3 digits are gone out of 10. So, therefore, 7 possibilities only are there here, 7, 7, 7, 7 are the possibilities for here, 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 here and here. So, total this cardinality will be 7 raised to 5, right. Now, we can substitute in that formula, namely what is the cardinality of A1 complement intersection A2 complement intersection A3 complement. Clearly, the student have already understood that this is what we are looking for. Why? Because this corresponds to those numbers which have a 2 in among their digits, right, because A1 was those numbers, there was a set of those numbers which does not have 2 in it. So, A1 complement will be those numbers which have definitely have a 2 in it. Similarly, A2 complement will be the set of those numbers from the universe which have a 3 in it among the digits, right. Similarly, A3 complement will be the set of those numbers from the universe which have an 8 in it. So, this intersection will mean these are the numbers from the universe which have 2 and 3 and 8 among their digits, right, and this we know how to calculate. Now, this is universe minus universe is so called alpha 0, which is 10 raised to 5 minus this alpha 0, right, minus k choose 1, k choose 1 is 3 choose 1 here, k equal to 3, 1 2 3. So, that is 3 into what was this, the cardinality of each ai, which is essentially alpha 1. We have written alpha 1. Alpha 1 is, as we have seen before, it is 9 raised to 5, right. So, and then next is plus k choose 2 into alpha 2 every pair, right. K choose 2 is 3 choose 2, 3 choose 2, 3 choose 2 is again 3, right. We can write it as 3 into 8 raised to 5, because alpha 2 is 8 raised to 5, we have already seen that. And finally, we will get 3 choose 3, k choose k, right. So, k choose 3, where k equal to 3 here. So, that is 3 choose 3 into alpha 3, right. Alpha 3 is 7 raised to 5, as we have seen, right. So, this will be the answer, right. So, here is a method to there is a method to find this one. Okay, so we have used inclusion exclusion to solve this stuff. Okay, so now what we do is look at the next problem. So now we take a general question: determine the number of 10 combinations of the multiset T equal to 3a 4b 5c, 3a 4b 5c. So, this is a multiset, right. So, let us consider this multiset. Yes, 3a, this notation we had seen, that means 3a means we have a 3 times here and then b 4 times here, right, and c 4 times here. This multiset, from this thing we need to create 10 combinations. 10 combination means we need to select 10 things out of this, right. We had considered this problem before, and then we know that the issue is that at the time we were saying that, so if each of this a, b, c all were repeating infinite times, right, and we want to make r combinations, right. That means there is no restriction on how many times I can take a certain type of thing, and then there are, we want to make r combinations, and then there are n type of things, then the answer is r plus n minus 1 choose r. This is what we did elaborately in the, when we studied combinations with repetition or combinations of the multisets, right. So, but here what is the difference? The difference is that, of course, these a's are not, we cannot take a's any number of times. For instance, if you want to make a 10 combination, the combinations of the form a, this 10 times a is not allowed, 10 a's are not allowed, not even 5 a's are allowed here, because we have only 3 a's, sorry, not even 4 a's are allowed, right. This kind of combination, this kind of selections are also not allowed, right. So, this is one issue. The repetition numbers now is limited. Of course, we really did not need infinity to use the other one, because when we are talking about 10 combinations, we just need 10 a's. If we had everything 10 at least, then we would not have noticed that repetition number is not infinite, because see, we will, whenever we want to take an a, there will be an a, because we are only taking 10 things out of it, and as long as 10 things are available in the 10 a's are available in the multiset, a's will never run out of when we try to make a selection. So, we can make all possible selections the way we want. So, if all type of things in the multisets had at least r, repetition number is r, in this case r equal to 10, then we could have used the earlier formula, right, namely r plus n minus 1 choose r. In this case, it would be r being 10 and n being 3, it would be 10 plus 3 minus 1 choose 10, right. That means 10, 12, choose 10. This would have been the answer, right. But unfortunately here we are we do not have that facility. We have only 3 A's. We in case if you try to take more than 3 A's, multi-set will not have that many A's. So what will we do now? This is a new type of question. So instead of looking at the most general question where we say that oh, okay, we have a multi-set with n1 A's, n1 A1s and then n2 A2s, we can look at this general situation of case. But instead of discussing it first itself, we will just take examples for 3 A's are there and 4 B's are there. So very special case. This is enough to illustrate the point, and then 4 C's are there. This is so yeah, this is more quite enough to illustrate the point. So later we will discuss okay what will happen in the general case, right. So the key thing we want to tell here is that in this situation we can use the inclusion exclusion principles to get an answer, right. So of course this is this will give you a rather complicated formula which is spit out by the inclusion exclusion idea. So not a very neat formula like the one we wrote in the repetition number equal to infinity case. So namely something like this may not come. We will use this formula to get the answer for this thing. So how will you formulate this question? Of course the universe now is considered like this. So the universe is that of suppose we had infinite repetition numbers, there is no restriction that only 3 A's are there, only 4 B's are there, only 4 C's are there, or we just assume that there are 10 A's, 10 B's, 10 C's, right. In infinite number of A's and B's and C's also you can assume, right, it does not matter. So what we do is right, what we do is we take that as the universe. For instance, all possible 10 combinations when there is no restriction on the repetition numbers, right. 10 combinations when there is no, so that is as we have seen, that is 12 choose 10. How did we get it? We applied the formula r plus n minus 1 choose r, where r equal to 10, n equal to 3. So this is the universe cardinality. This will be the cardinality of the universe. Now what is the cardinality of I mean what we do is we want to get rid of the bad things from the universe, right. We want to only select from the universe those 10 combinations which satisfies our requirement, namely that is 10 combinations which can be made out of this multi-set. That means any 10 combination which has more than 3 A's in it should be rejected. Any 10 combination which has more than 4 B's in it should be rejected. Any 10 combination which has more than 4 C's in it should be rejected. This is what we have to say. So to capture this thing, we will again define properties P1, P2, P3, and P1 is what this is the property that, so the properties are defined on members of the universe. That means on a let say yeah, we will take a 10 combination C, right, P1 of C. That means the 10 combination C has at least 4 A's, right, because we have only 3 A's available in the multi-set given to us. 4 A's are not allowed, but we are defining a property that this is an undesirable property. We are defining the undesirable property, right. We usually define the undesirable properties. So when we want to apply the exclusion inclusion principle, right. This is the first undesirable property, namely the 10 combination, say C being a 10 combination, it does not have it has at least 4 A's. So it does not satisfy the required property. Similarly, P2 will be the property that 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 the 10 combination C has at least 5 B's. Recall that in the multi-set given to us there are only 4 B's. Therefore, if we take 5 B's, then if a 10 combination has 5 B's, we have to reject that 10 combination, right. So, therefore, this is a second undesirable property, and the last and third and last undesirable property is that the 10 combination C has at least 5 C's, right. This okay friend, this C and C, this should not be considered. This is a capital C here just to denote the 10 combination, and this is just that letter C, right. So, these are the 3, and of course, we as usual we will define A1 to be the set of 10 combinations from the universe which has property P1, namely those 10 combinations from the universe such that they have at least 4 A's in it. Similarly, A2 is the set of those 10 combinations which are property P2, that means those 10 combinations from the universe which has at least 5 B's in it, and A3 is the set of 10 combinations from the universe that has property P3, right. So, now it is very clear that what we are looking for is this A1 complement, A2 complement, intersection A3 complement, because so since A1 means those 10 combinations from the universe which has at least 4 A's, A1 complement means those 10 combinations from the universe which has at most 3 A's. Similarly, A2 meant the 10 combinations from the universe which has at least 5 B's. So, A2 complement means the 10 combinations from the universe which has at most 4 B's. Similarly, A3 complement would mean the 10 combinations from the universe which has at most 4 C's. So, then those 10 combinations in the intersection of A1 complement and A2 complement and A3 complement will be the ones we are looking for, namely those 10 combinations which has at most 3 A's, 4 B's and 4 C's, right. And this clearly is coming from the multi-set S, right, given to us, right. That would be valid 10 combinations which can be formed from the multi-set given to us, right. How do we estimate this thing? We apply the inclusion exclusion principle, and we know this the cardinality of this thing is given by the cardinality of U minus sigma I equal to 1 to 3 here, and is k equal to 3. So, AI cardinality, then we have to plus for every ij. So, AI intersection AJ we have to find. So, there are choose 2 of them, namely 3 of them. So, we have to add it, and then finally minus. So, for every ijk. So, here in this, because there are only 3 of them, we have only one set here, right, namely A1 intersection A2 intersection A3, right. This is what. So, we just have to now we have to verify whether we can find out the values of this, the values of each of cardinality of AI, the cardinalities of AI intersection AJ for every pair I and J, and that is all we have to check, right. So, let us see how we do this thing. So, the cardinality we know, namely that was 12 choose 10 as we calculated. It is just assuming that there is infinite repetition number, we just found out the value, right. So, by applying the formula we studied earlier, namely R plus n minus 1 choose R. Now to find the cardinality of AI, say A1, let us take. A1 is what? A1 is the set of 10 combinations such that there is at least 4 A's in it, at least 4 A's. So what we do is we set a bijection between the set of 10 combinations, right, combinations of A, B, C with at least 4 A's, and the set of 10, because 4 A's we remove, that means 6 combinations of A, B, C without any restriction. Here we do not keep any restriction, we do not say that there should be. So, there is a bijection between these two sets, this set is A1 only. Why is it so? This you can say write as A1 dash. Why is this same? Because you know, if you get a 10 combination with at least 4 A's in it, say some 4 A's in it with some B's and all. So, what we do is we just remove those 4 A's and take the remaining, just remove 4 A's from that and take the remaining, that will be a 6 combination using A, B, C. So, now there can be B's, A's and C's, sometimes A's may be 0 whatsoever, right. So, we will get a 6 combination. Now, so therefore, for every 10 combination we can create one unique 6 combination like this by throwing away 4 A's, right, from that, because there are already 4 A's in this kind of combinations, in the 10 combinations in A1. Conversely, suppose you get a 6 combination of ABCs where there are A's and B's and C's, and the repetitions, the number of times A repeats may be 0 or 1 or whatever. What we can do is we can add 4 A's to it, right. So, we will, what we will get is a 10 combination, because this is 6 combination, we add 4 more A's to it, we get a 10 combination where there are at least 4 A's, right. We make sure by adding 4 A's into it, that becomes a 10 combination with at least 4 A's in it. So, there is a, we have pointed out a bijection between the two sets. So, instead of counting this, we can count this A1 dash namely, and this is easy to count. Why? Because we know the formula for that, because we here we do not have any restriction on how many A's can be there and all. So, this is just that any repetition number is allowed. So, therefore, that is we can use R plus n minus 1 choose R formula, here R being 6, right, this being 3, n being 3 of case. So, that is 6 plus 2 8, choose 6, 8 choose 6 will be the number. Similarly, so therefore, A1 cardinality of A1 is 8 choose 6. Now, if you want to find A2 cardinality, A2 cardinality is what? We are talking about the number of 10 combinations in the from the universe, 10 combinations, right, 10 combinations such that there are at least 5 B's in it. By following the same argument as before, what we can do is, this is A2, right, we can set up a bijection between A2 and say A2 dash, where A2 dash is the 10 combinations of ABC, not 10 combinations, here we take, because 5 B's are there. So, 5 combinations of ABC. What we do, when we for any 10 combination from A2, that means any 10 combination which has at least 5 B's, we can delete those, delete 5 B's from it, we can remove 5 B's from it and we get a 5 combination then, right. And that does not have any restriction, that means it is it can have even 0 B's, right. So, we are not saying that there should be this many A's or this many B's, it is unrestricted. So, therefore, this Similarly, if you have some 5 combination of ABCs whatever, we can add 5 more B's to it and make a 10 combination. So, definitely with R equal to 5 we will get the answer to be 5 plus 2 choose 5, that means 7 choose 5, right, putting R equal to 5. Similarly, if you want to find A3 cardinality, that is also easy, because now again the restriction is that we need at least 5 C's in it. So, we set up a bijection between that set A3 and A3 dash, where A3 dash is the 5 combinations of ABC, right, 5 combinations of ABC. So, as before what we can do is when we have a for any 10 combination in A3 which has, of course it has at least 5 C's, we remove 5 C's from it and we get a normal 5 combination of ABC, right, and this and reverse also. Therefore, A3 cardinality can be found by finding A3 dash cardinality. Here it is a, we can apply the formula with R equal to 5 and N equal to 3, and we again get from this thing 5 plus 3 minus 1, that is 7, choose 5, right. So, we can easily find the cardinalities of A1, A2 and A3, right. Now, we want to see whether we can find the cardinality of A1 intersection A2, right. Is it possible to find the cardinality of A1 intersection A2? What is this A1 intersection A2? A1 intersection A2 is the set of 10 combinations which has at least 4 A's in it and at least 5 B's in it. Now, what we can do is we can let this be called B. We can set a bijection between B and B dash, where B dash is defined as the 1 combinations of ABC, right, 1 combinations of ABC. Why is it so? Because see, you take any 10 combination with at least 4 A's and 5 B's, and from that you just remove 4 A's and 5 B's, and we end up with, because 10 things were there, 9 things are removed now. So, just remaining 1 we will take, that will correspond to the 1 combination in B dash, right, that is the bijection we are setting up. And reversely, if you take any 1 combination of ABC, that can be an A or a B or C, whatever, we can add 4 A's and 5 B's on top of it, and we will get a 10 combination. So, which satisfy the property that there are at least 4 A's and 5 B's, right. And this is indeed a bijection, therefore, it is a bijection between, we just have to count this, and this number is easy to find using the formula, namely this is R plus N minus 1 choose R, with R equal to 1, N equal to 3. So, this is just 3 choose 1 equal to 3. Oh, so, even without formula we can easily find this thing, because these are just 1 combinations of ABC. So, only 1 combinations are either A or B or C, right, there are 3 such things. We can see that here also we could, without going through this bijective argument also, we could have easily inferred that A1 intersection A2 cardinality is indeed 3, because we need 4 A's 5 B's. We already finished off 9 things, right, by compulsion. So, forcefully we had to take 9 of them, right, 4 A's and 5 B's. The last thing only we had a freedom to select. So, we can select either A or B or C. There was 3 ways to do it. Therefore, it was not at all difficult to infer that this cardinality of B is equal to C. That means this is 3, right, this is 3, right. So, similarly, we can find the cardinality of A1 intersection A3. What is it? There should be at least 4 A's and 5 C's. So, that means 9 things are already taken in the 10 combination, only 1 can be taken. The same argument as before, we can do it in only 3 ways. And if you want to find A2 intersection A3 cardinality, this, what is this set? This set is the set of 10 combinations where there are 5 B's and 5 C's. That can be done only in one way, because now 5 B's 5 C's, already 10 things we have selected, right, at least 5 B's and 5 C's should be there, then this should be 1, right, there we cannot do anything, right, we can only leave it as such. So, that is only 1, right. So, A2 intersection A3 is 1. Now, if you want to look at the last thing, so we got all the terms required except the last term, namely A1 intersection A2 intersection A3. How do we find the cardinality of this thing? This means we need 4 A's in the 10 combination, 5 B's in the 10 combination and 5 C's in the 10 combination. So, this already asks us to take 4 plus 5 plus 5, 14 things, but we are only talking about 10 combinations. That is not possible, right. So, this cardinality has to be 0, right, this has to be 0. Right. So, therefore, we can substitute whatever we calculated up to now in the formula we set up using the inclusion exclusion, namely this formula. Here we have 10, 12 choose 10, here we know what so all the numbers we had calculated, and here all the for all the pairs we had calculated the cardinality, and the final thing was 0, right. So, we can estimate it. It is not important to do the computation. So, we leave it to the student if at all, that is definitely not important. So, we just need to know the technique, right. So, now we will look at the next question, or not next question, because this was an important thing. So, therefore, we will look at the generalized form as I was telling in the beginning. So, the number of R combinations of the multi-set N1 A1, N2 A2, sorry, this is a small mistake here, and so N2 A2. So, this you discard this portion. So, that is N2 A2 and N3 A3 and NK AK, right, equals the number of integral. So, fine. So, I will explain it using the, see, this is the multi-set we are interested in, N1 A1, N2 A2, and this is NK AK. There are k type of things, and then each of them are coming ni times, AI is coming ni times in the multi-set. Now, we want to make R combinations, right. So, as we have mentioned before, or all, I mean many times we have mentioned now, if each ni is greater than or equal to R, then it is as good as each saying that each type has infinite repetition number, because we are only making R combinations. For instance, if I want to take some AI, we will get R copies of it. So, we have no restriction, so no constraint. Therefore, we can use that formula R plus here k types, k minus 1 choose R. On the other extreme also is easy. For instance, namely there N1 equal to 1, N2 equal to 1 and Nk equal to 1. Suppose each of them, all of them are 1, then also is easy. It is just saying that because this, though we call it multi-set, then it is just a set A1, A2, Ak, no repetition, right. So, how many R combinations we can make out of S? That is our simple k things out, k things are there, out of that R combinations are to be made, that is Nk choose R, that is very easy. So, the problem is when these some ni's are in between R and 1, it is bigger, I mean some ni's, right, are bigger than 1 and or smaller than R, right. Not all of them are R, not all of them are, so not all of them are R or bigger, not all of them are equal to 1, right. In this case only we are worried, we have to, right. So, that is the situation we explained. We explained elaborately using k equal to 3 k's we took, and then showed how to apply the inclusion exclusion principle. But only thing is when k is a big for instance, not we in our example it was 3, suppose k was much bigger, we have to write a very long formula using inclusion exclusion, and each individual term has to be estimated. Definitely it doesn't, it is not very you know, it is not very neat, it is not, sometimes it may not be useful, because but if by a computer probably you can program it, because okay, every step is implementable. It is not that we have to be clever at some point, we know what to do at each point, but we will finally we can do, right. If we have a computer we can do it, but then right. So, yeah, but the technique definitely helps if you really desperately want to find the number, right. We do not have any very nice elegant formula for that, like in the extreme case, right. Now, what we want to look at is, so something which we have already seen, namely its equivalence to this x1, this solutions of integral solutions of x1 plus x2 plus xk equal to r, right. So, that is what we will see. So, we will again consider that this equation x1 plus x2 plus x3 plus xk, that is equal to r. Say we are interested in the situation each xi is greater than or equal to 0, each xi, right. For each xi we have this condition, namely 0 greater than or equal to xi, then that is as good as saying that we have already discussed it. It is as good as saying that we want to find the R combinations of k type of things, where each thing can be taken infinite times, right. So, that is we had described it before, what is the correspondence between this and all. These are things, right, and this k type of things, right. That is what we had discussed in the earlier class. And we had also told that this was equivalent to a balls and bins problem, where we wanted to distribute R identical balls into k distinct boxes. That means boxes which can be differentiated from each other. That means boxes, labeled boxes, right, the boxes which can be distinguished from each other, right, first box, second box, third box, kth box. So, that is also where we allow some boxes to be empty, but this R ball should go into those boxes, how many ways we can distribute. But we never considered the situation where we also have an upper bound on this xi, namely for each xi is upper bounded by ni, some ni, where this ni is not r or more, right, it is ni being less than r. So, as we can easily see, this corresponds to the earlier situation, namely when R balls are to be distributed, and sorry R, so we have to make R combinations, and but we have a restriction that the ith type of thing can be selected only at most ni times, right. That is what this is saying, because you remember the bijection was that the value which x1 gets will correspond to the number of times the first type of object is selected to make the R combination, namely x2 would correspond to the number of times the second type of object is selected to make the R combination, and similarly xk would correspond to the number of times the kth type of object is selected to make the R combination, right. Now, this extra restriction means that the xi is less than or equal to ni, that means xi, the ith type of thing cannot be taken more than ni times, maximum ni times only it can be taken. That is what we considered in the last example, how we can use the inclusion exclusion principle to do that, right. So, in the balls and bins case, so this xi would correspond to the number of balls that we place in the ith box, right, in the ith box. So, when I say xi is at most ni, it would correspond to saying that in the ith bin, ith box, we can place at most ni balls. We cannot put more than ni balls in the ith box, that is what it means. So, we should remember these 3 equivalent problems, because so that see, when a particular situation comes, we may be able to model with the most convenient model, or we may be able to identify. These are all equivalent thing, either are identical balls being placed in k labeled boxes, right, with various restrictions, like the boxes has to be non-empty, empty, all these things we had discussed before. Now, we are telling the extra restriction that a particular box, ith box, can hold only maximum ni balls, right. So, that is what in the equation form, this is what is happening. Here we xi is at most ni is what it would correspond. Similarly, in the R combination case, it is equivalent to saying that the Rth type of object can be taken at most ni times to make the Rth combination, right. So, yeah, we just describe this correspondence. The next question we want to consider is in this line. So, we put more restrictions and see whether we can solve it. We are stretching ourselves further. So, what is the number of integral solutions of the equation x1 plus x2 plus x3 plus x4 is equal to 18 that satisfy 1 less than equal to x1 less than equal to 5. Here, instead of 0 less than equal to xn, we are putting 1, upper limit is also added, right. So, and also here we are saying minus 2 less than equal to x2 less than equal to 4. Up to now we were always saying 0 less than equal to x2 less than equal to something. So, but here allowing minus value, and the third variable has the correct range, 0 less than equal to x3 less than equal to, so some 5 upper bound is introduced. Similarly, the fourth one has upper and lower bound, the lower bound is not 0. So, how will you manage? We know mostly how to do this thing. The technique, we have already discussed the techniques. The only thing is the upper limit, actually the upper limit is the new one, that we have to take care of by the method we discussed in the previous problem, namely the inclusion exclusion principle. This one we will discuss in the next class.